Hello everyone, welcome back to another lecture on electricity and magnetism. And today's lecture is lecture number 26. In the previous two lectures, we have seen an overall idea about the vector calculus and the physical meaning of the equations that are written down, such as the gradient, divergence, and the curl. So the last two classwork will give you a fairly good idea of what the vector calculus is all about and how the equations in the vector calculus will look like. So we have basically seen the differential operators and we have also seen some integral operators, and we are now ready to see some of the properties. Properties means some kind of equalities between one integral and another integral, or one differential operator to another differential operator. There are some equalities are there. Such equalities are known as theorems. Most of the time they are referred to as theorems in vector calculus, which means that these theorems are going to be very helpful in simplifying certain equations. Okay, that's a very important point. What is by theorem? We are not going to do the proof of the theorem. That is not the objective in electromagnetism. Okay, proving the theorem and then solving some more mathematical examples, that will be done in the mathematics course that you are studying. So in the case of electromagnetism, we are going to take those important results in vector calculus, what are known as the theorems, and then apply them to the experimental observations. So where are you going to apply these vector calculus rules is, you are going to apply to the experimental results. What are the experimental results that you have in electromagnetism? You already know they are the Coulomb's law, first one. The second one is the Biot-Savart law, giving you the experimental information of the magnetic field. That is the second experiment. The third experimental observation or the third experimental discovery is the Faraday's law, which means that generation of certain electric potential due to fluctuating magnetic field. That is where Faraday's law. And the last one would be the Ampere's law. So these four equations, or we say that these four experimental observations, all of them are experimental observation. It appears that the things are disconnected. Disconnected means you feel that the Coulomb's law is something different, and Biot-Savart law and Faraday's law, they all some different experimental observations, and you feel that they are not connected to each other. Okay, that means only because of the experimental results that you have, you do not have any reason to ask for any connection between the Coulomb's law and Faraday's law, Coulomb's law and Biot-Savart law, and Faraday's law and the Ampere's law. If you ask such question, what is there any connection between them? Only from the experimental evidences and only from the experimental observations, there is no idea on how these things are interconnected. Sometimes you may even feel that there is no connection between them. They are all different experiments, and one experiment has nothing to do with another experiment. That is how you will generally feel if you are going to have only experimental evidences and only experimental results. So this is where the vector calculus now comes into picture. Now the mathematical properties of the calculus of the vectors provide more detailed interconnection between different experiments. That is the primary reason why the vector calculus has to be introduced in the electromagnetism, and that is the one which is going to give you more physical insight into the interplay between one phenomenon and the other phenomenon. That means that the electric field and magnetic fields are interrelated to each other. Faraday's law and Ampere's law are once again interrelated. So all the four of them, in terms of the laws, are interrelated. Even though there are four laws are there, ultimately you are going to have two fields. One is the electric field and the other one is the magnetic field. Only two fields are there. The laws can be four. That is, laws means Coulomb's law, Ampere's law, Biot-Savart law, Faraday's law. So in terms of that, you may be having four different observations, but however, ultimately you are going to have two fields. One is the electric field and then another is the magnetic field. And why these fields got generated, if you ask the question, and we have a primary reason. Electric fields are generated because of the presence of electric charges. This is the first point. Second point is, similarly, magnetic fields are generated because of the existence of currents. If the electrical currents are not there, then you will not be having the magnetic field. This is what we understand using these experimental observations. So we have two sources. Two sources means electrical charge is one source and electrical current is the second source. These are the sources. Because of the two sources, you have two fields. One is the electric field and the second is the magnetic field. And that's all about it. The electromagnetism is going to deal with electric and magnetic fields due to the presence of the electric charges and the electrical currents. That's all. And now this information is going to be written down using the equations of vector calculus, because electric field is a vector quantity and magnetic field is also a vector quantity. See, that is the reason why we can always apply the rules of the vector calculus or the theorems of the vector calculus. Why we can apply such things is because electric and magnetic fields are vector quantities and therefore they have to be obeyed by the electric and magnetic fields also. So that is the reason. So keeping this as an introductory or keeping this as the overall picture about the electromagnetism, coming to the discussion in the last class work, we have actually written down the Gauss divergence theorem at the end of the last class, and I said that using this particular Gauss divergence theorem, we are ready to proceed further to discuss the Gauss law in electrostatics. That is the place where I stopped in the last class. So let us now continue that. Let us go to the board and then continue what is the discussion. So let me first of all write down the Gauss divergence theorem that was available at the end of the last class work. So the statement is simple. So once you understand and write, it will be simple rather than memorizing. The Gauss divergence theorem statement is the following. The volume integral of, so therefore you write down volume. So dV is the volume. So volume integral of, so you put an integral here, and which means that the integral is supposed to be a triple integral. So whether you write three of them or not, it is actually a triple integral. So the volume integral of, that is called a triple integral of the divergence of a vector field. So let A be a vector field. Okay, so let us put a bracket like this. So the volume integral of the divergence of the vector field is equal to the normal component of that vector. So how do you take a normal component? Is you have to take a dot product with a surface. Okay, otherwise you won't get the normal component. So that is the meaning. Is equal to the surface integral of the normal component, because the normal component means when a particular quantity is a vector quantity, it is a three-dimensional object. Okay, so that means certain thing is flowing like this. So for example, if a vector field is going in all possible direction like this, for example, these are the directions of the vectors. That means A vector. This is what we say the A vector. Because it is existing in all possible places in three dimension, you want to consider only a particular unit surface. That means the surface area should be 1. So this will be the surface, which if it is very small, we can represent it by the surface ds. So I will now represent it by the shading here, and that is what we mean to say the surface area. So in the surface area, since this is going in this direction, it won't enter into this surface. Similarly, the one which is going exactly perpendicular to the surface, the entire vector will penetrate. Some of them which are crossing, some of them which are moving at an angle. For example, if something is moving at an angle like this, then this particular field will not be penetrating into the surface. And if at all, if it penetrates, only a component of that will penetrate. That means you will have to consider the cos theta component or sin theta component, depending on how you measure the angle theta. So that is clear. And in the simplest language, you can understand that if you are going to consider a surface like this, then the field has to be perpendicular to this. That is what we mean to say. If it is the case, then we say that the entire A vector Entire A vector, entire is very important. Entire A vector is passing through the surface. If it is not, if the A vector is not like this perpendicular, but instead if the A vector is like this, if it is like that, then entire A vector is not passing through this cross-sectional surface, but rather what is passing through this particular surface is only A dot ds. That is what we mean to say. So the meaning of A dot ds represent how much amount of the original vector A is passing through the surface ds. That is the answer. A dot ds tells you that. Okay, if something is going in a cross direction like this at an angle, then the entire vector won't enter into, or it won't penetrate into the differential surface ds, and therefore only A dot ds is the quantity that is penetrating. So that is the reason why we write A dot ds. And the theorem says, the statement of the theorem says is that if you are going to evaluate a volume integral like this, and if you are evaluating a surface integral like this, the theorem says that these two values will be identically the same. That is what is the statement of the theorem, and this theorem is what is known as the Gauss divergence theorem. Now here we can write down that this is a surface, and where the integral is going to be performed on the volume that you are going to consider. And in the last class I already explained an important point, that the volume that you are going to consider is connected to the surface. You have to first of all decide what is the object that what is the region. Suppose if I am going to consider the spherical region, then automatically the surface of the sphere is the ds. So surface of the sphere and volume of the sphere, so they are connected to the same geometrical object. Okay, volume cannot be something different and the surface cannot be something different. Okay, such a thing is not, there is no meaning for that. So therefore the important point to be noted is that this is the surface bounded by the volume. Okay, so this being the Gauss divergence theorem, now what we can do? So now we have the Gauss law like this, which is already established a few classes back. Okay, we have the Gauss law like this. Namely, the divergence of the electric field is equal to rho divided by epsilon naught. This is what we have. Now what we will do is, because divergence is there in this particular Gauss law equation, and there is a divergence in the Gauss divergence theorem, let us apply, or let us evaluate the triple integral. That is what we mean to say. So we will do that. So let us evaluate the volume integral according to the Gauss divergence theorem. We'll evaluate this for the Gauss law. So what will you get? You put this triple integral of the del dot E. Del dot E is what is there on the Gauss law. That is what we are going to write. And then this has to be performed over certain volume. And then that will be equal to, on the right hand side also, same volume integral you will have to evaluate. That means we are going to take the volume integral on both sides of the Gauss law. That is the meaning. So therefore you will have to write down the same volume integral on the right hand side, and the right hand side is rho divided by epsilon naught multiplied by the volume dV. And then we can now easily simplify, because this 1 divided by epsilon 0 is a constant. Then ultimately we have the triple integral of the rho into the dV. And now if you remember what is rho, then the calculation is very simple. Rho is the charge density. And you already know the definition. Charge density means charge divided by total volume. Total charge divided by total volume is the charge density. If it is the case, how much will be rho times dV? This quantity should be equal to total charge. So this is very basic. The very beginning of the electromagnetism, we have learned this. Therefore, rho is the charge density, which is spread over in a particular volume V. V is the total volume. V I will write here. V is the total volume. dV is the elemental volume. So the charge density rho is spread on a particular volume dV, so that it covers the entire volume V. if it is the case, what is the meaning of the integral of rho dV? So integral of rho dV will give you the total amount of charge that is present. So therefore, this gives you the total charge which is present. So I'll write down that this is Q total. That means the total charge which is present inside the volume capital V. That is the meaning. Then I'll write down divided by epsilon 0 is as such, which means that the evaluation of the integral is quite simple and the right hand side has been simplified. And for the left hand side, what you do is, let us again keep the board in the original place. For the left hand side, what you do is, you now see the Gauss divergence theorem. It says that the triple integral can be converted into, or we say that it is equivalent to a double integral. So that is what we mean to say. So therefore, this particular triple integral, we will write down as the double integral because these two are same. You see how we are converting. This particular triple integral is equal to a double integral according to the Gauss divergence theorem. Therefore, I can write down A dot Es. But now what is A? A is our electric field E. Therefore, E dot ds, where the integral has to be performed in a closed surface. So remember that in yesterday's class I told you that the surface should be closed. Only when the surface is closed, you can define some volume. That is what in the last class also I explained. When you have a cube, all the 6 sides of the cube should be closed. That is your box. If you open one side of the box, then if you ask the question what is the volume, you cannot answer or you cannot find out what is the volume, because when one side is open, then the entire remaining space is to be added for the volume. Okay, that goes to infinity, right? So you must close it. If you don't close it, then the total volume goes to infinity. So now you understand why we have to close. Only when the surface is closed, we will define volume. Otherwise, volume cannot be defined. And that closed integral is what we put a circle here. So you see a circle, right? That is called a closed integral. And that is what exactly here also the same meaning comes into picture. And according to the, or based on the Gauss divergence theorem, this particular volume integral can be rewritten because of the equality here, can be rewritten as a double integral. And that's what we have written here. This triple integral has been converted to a double integral on the left hand side. On the right hand side, we directly evaluate the triple integral without making use of any conversion. And ultimately, we therefore got this expression that the closed surface integral, I'll write down that this is a closed surface integral of the E dot ds is equal to the Q total divided by epsilon naught. As you see here, I have written only one integral instead of the double. And the reason you already know. There is no need to write double integral, triple integral, etc. The presence of the ds here clearly tells that it is a surface, and therefore the integral is a surface integral, which means it is a double integral. So those things goes by understanding, and there is no need to write there is no need to show the second integral which is present here. But if you really want to put it, you can always put, there is nothing wrong like this. You can always put the double integral, but it is not compulsory because the meaning is clear, and therefore the number of integrals you need not have to worry. So we got the final answer now. Now instead of saying it is total, a better word instead of total is the word enclosed. So I'll write down this is enclosed here instead of saying total, because total charge means you get a doubt. Total means what are all the charges that I have to add so that I will get the total. That doubt will come. If it is enclosed, such doubt will not come. So I will now explain what is the meaning of enclosed. And the left hand side is same thing. So therefore the closed integral, namely the closed integral over the entire surface where the charges are present dot ds equal to this. And this is the result that we are interested in. And this is what is known as the integral form of the Gauss law. So this is the reason why I was waiting until we explain a little bit about the vector calculus. So once you have some idea about the vector calculus, differential operators, integral operators, and a few relations. Relation means a few theorems in vector calculus. Understanding the electromagnetism becomes now easy, which means that you basically rewritten the Gauss law in a different style, and we say that this particular form is known as the integral form of Gauss law in electrostatics. That is the meaning. And next thing is that why it is called enclosed here is that in order to understand the meaning of enclosed, you ask the question, what is this ds and what is the surface here? So this particular surface is, you'll have to understand this. This is the surface over which the integral is to be evaluated. That's the meaning. So if you are going to consider some kind of a diagram like this, let us take a simple situation of the case of the cube so that it is easy to understand. If I am going to have a cube like that, like this, then you can easily verify that there are 6 surfaces are there, which are only for one or two surfaces I will show here. That this is the right side surface, and then this one will be the left side surface that is there. Like this you have, isn't it? Similarly, you have the front face, then you have a top face here, then you have a bottom face here. So there are 6 surfaces are there for a particular object. So that is clear. Now what we are trying to say is that within this box, so that is the important point. We say that inside this particular box is a particular example. It need not be box, right? In general, it can be of any shape, spherical, cylindrical, even that is not also required. It can be any kind of shape, but inside that particular object, you will be having charges. That's what we mean to say. So here some charges are present, so that it is called charge density. So these things are this particular thing is the charge density you have. So you are basically asking a simple question that what is the meaning of the Q total here? So here we have written the word total. Total means what are all the charges that I have to add up? That is the question. The answer is you add those charges that are present inside this particular object. That means the place where you are going to perform the integration. You are going to put the limits of the integration, right? Limits are, what are the limits? Left wall. This is the left wall or the left side of the edge. And this is the right side wall. So these are the two limits for the x-axis. Similarly, if you take the front face and the back side face, you get the limits for the y-axis. Similarly, the bottom face here, this is the bottom face that you have. And then here you have the top face. So the bottom face and the top face will give you the limits for z. So x limits, y limits, z limits are there. So those limits will define what is the closed surface. So inside this closed surface, you are going to find out what are all the charges present in the system. And that is what we say enclosed. So how much amount of the charge is enclosed inside the closed surface? That is the meaning. Okay. So the meaning should be now clear. The word enclosed therefore means that, here I can write down. So enclosed within, we can say within or we can say inside. Enclosed inside the closed surface. Okay, so that is the meaning of the enclosed that is present here. I'll put this connection. So, and that's all. Now we have the Gauss law in two forms. The differential form of the Gauss law and the integral form of the Gauss law. What is the differential form of the Gauss law? That is what we started. The starting point is itself the differential form of the Gauss law. So where do you have it? So this is the one. So this is the differential form of the Gauss law, and now we have converted into the integral form of the Gauss law. Now, why do you want to have these two versions? As I already told you, that one of the version will be more useful when compared to the other one when you are dealing some problem. Not for all problem. For some problem, differential version will be very useful. For solving some other problem, integral version of the Gauss law will be very useful. So in particular, let us see how easy it is to get the electric field if we are going to use this particular Gauss law. Let us see how easy it is. Now, as an example, you consider a sphere of radius A. So you have a sphere of radius. It can be any, A or capital R, let us take. So you have a sphere of radius capital R, and inside this particular sphere, at the center of the sphere, let us assume that you have a plus Q charge. So at the center of the sphere, you have a plus Q charge. What is this sphere is that, remember, this is the place where geometry enters into picture and you don't have the real object. So this clarity should be there for you when you are evaluating the Gauss law using the integral form. So the clarity, let me explain once again, that while you are performing the calculation of the electric field using the Gauss law, that is exactly the example 1, there are two things are there. One is a physical object or a physical quantity. The second one is a geometrical object. Geometrical object is different, physical object is different. If you have a cricket ball, that is a physical object having a spherical shape. You are actually having an object with you. It is occupying some space, you can feel it. That is called a physical object. Geometrical object is not visible to you. You can't even feel the existence of that. If I say that I have a straight line, or if I have a sphere, you take the sphere itself. Suppose you say that I have a sphere, mathematical sphere, okay? A sphere means not in the form of a physical object. Physical object means it should be made up of some material. If you have a rubber ball, it is made up of rubber. It can be made up of cork, then it is cork ball. Or you can have a balloon in the shape of the sphere, okay? So then you need to have a rubber. So these are the physical material. These are called physical objects. Mathematical sphere, if I say sphere, in which material sphere is made up of means there is material itself is not at all required. Okay, there is no material required. Therefore, you can always imagine that the spherical shape is what you have to imagine, or the shape is what you have to bring into your mind. And sphere itself does not exist. Therefore, that is not visible to you. And therefore, this is the very critical point that has to be noted down in understanding the calculation in vector calculus, or in general, any mathematics. This is what is the trick, or this is what is the idea that goes behind. Mathematical objects are not visible, and therefore this sphere which I have said is not a sphere that is made physically and that is located. We don't have any sphere. Therefore, this is a mathematical object. So this is a mathematical object, which means we are drawing a spherical diagram around it. That's all about it. Then what is there actually physically? What is there actually means only 1 plus Q charge is there at the center. That's all about it. Only 1 plus Q charge. One charge is there at a particular point. That's all matter over. That is only physics. After that, why are you drawing? Now the next question comes, then why did you draw a sphere like that? Is the reason here. So now you see, it is the closed surface we need. Here it is written closed surface. You can take any closed surface. You can take a rectangular box, or you can take a parallelepiped, or you take some kind of a prism. Everything is closed, right? Or you can take a sphere. You can take anything you like. That is the interesting freedom available in the vector calculus, because certain theorems in the vector calculus tells you that the shape of this particular object is not at all important. The shape is not important. What is important is whether the surface is closed or not. So this is the interesting point, and you have the freedom of choosing whatever shape you like. And we believe that evaluating the surface of this spherical one will be very easier when compared to taking some kind of a prism structure. You can also draw a prism around this particular charge, that is also a closed one, but then evaluating the total area around it, and then evaluating the normal component, E dot ds is normal component. So those things will become complicated. So we are now having the freedom of choosing whatever surface we like. And in this problem, we are choosing sphere as the surface surface, and therefore spherical surface is what we are going to consider. The reason is evaluating the normal component is going to be very easy. That is the reason. So there is a reason why we are choosing sphere also. Evaluation of the normal component is going to be very easy for the case of the a single charge there. Okay, these things are the reason why we are choosing the spherical object. This is fine. Then there are two things are there. The right hand side, you will have to put the total enclosed surface. So let us now see what is the aim of the problem. The aim of the problem is to calculate the electric field due to a point charge. That is the aim of the problem. And in order to do that, we need the right hand side of that. So this is a geometrical sphere. So let me therefore make it further clarity by writing here. So this is the geometrical construction. Even though I have explained it, let me write down so that you can also write down in your notes, so it will be easy. So the sphere is basically a geometric construction. Physically what is there is only a charge is there, and that's all about it. Okay, let us come to the RHS of the equation. What is the right hand side of the equation is Q enclosed, then divided by epsilon 0. What is the meaning of enclosed? Now you already know. I have a surface which is a spherical surface. Inside this particular surface, how much amount of the charge is enclosed? Means how much amount of the charge is present inside. That is the meaning. If any charge is present here, let me now show another situation. Suppose if you are going to have another charge here, for example, minus capital Q is there. Then here one more charge is there, minus, let us say 3 Coulomb charge is there. You have 2 more charges are there which are outside. So those things which are outside you should not consider for the calculation. That is the meaning of enclosed. So enclosed means what is the charge that is present inside the surface that you are considering. That is the meaning. So therefore, if at all anything is present, then we will not consider and simply you reject it. And ask the question how much charge is present inside. We see that only one charge plus Q is present. And therefore, we will be writing the total charge enclosed is equal to Q, and then divided by this epsilon naught will be this epsilon naught. That's all about it. And epsilon naught generally gives you information that this particular system is either kept in vacuum or it is kept in the pure air. Okay, there are no other dielectrics are present. That is the meaning of epsilon 0. If additional dielectric materials are present, then epsilon 0 has to be appropriately multiplied by epsilon r. Okay, so that is an additional work if it is required. Now right hand side is clear. Now we'll have to evaluate the left hand side of the Gauss law. So where is the left hand side? This one. That is, we will have to evaluate the closed integral of E dot ds. So if we evaluate this and then put an equal to sign, because these two are equal, then we will be getting the answer. So this will give you overall idea about how this Gauss law really works. So let us therefore evaluate the left hand side of the Gauss law, and which is equal to, so therefore we will now substitute that the closed integral of E is the electric field. That is the one which we are interested to calculate. Okay. So let us assume that we do not know what is the electric field generated by the point charge. This is another important point. You will have to catch the point. Okay, don't substitute the Coulomb's law equation now. You see, this is the critical point, very important point. Our objective is to evaluate the electric field. Okay, you should not say that I already know Coulomb's law and substitute that. If you are going to substitute that then Gauss law is not required. That clarity should be there. If you say that I will use the Coulomb's law, okay, fine, you use it, then Gauss law will not come into picture. If you are going to use the Gauss law for the evaluation of the electric field, then Coulomb's law should not come. So that clarity should be there, because it is only the Coulomb's law that has been rewritten now. Therefore, again, you should not mix up the things. So once you use the Gauss law now, we will now say that I do not know what is the electric field generated by the point charge, and therefore I will only write E here. That's all. I do not know what is E. It is to be calculated. But however, But there is another point is here. But however, if you know the symmetry of the field, so there is some partial information is required here. This is where the symmetry enters into picture. If the symmetry of the physical system is known beforehand, then Gauss law will help you to evaluate the magnitude. This is the second important point that you need to know about the Gauss law. So the clear distinction should be there. Okay. What is the advantage of the Gauss law? Answer is, the advantage is that we can quickly calculate, or we can calculate the electric field in a very easy way if and only if you know the symmetry of the problem beforehand. Beforehand means before solving the problem, you should have an idea about the symmetry of the electric field. If it is so, is very important. If it is so, then the calculation of the electric field using the Gauss law becomes very simple. Okay, otherwise what happens? Suppose I do not know, I don't have any idea about the symmetry of the electric field. If it is the case, then what happens is, if it is the case, this Gauss law is not going to help you, and therefore you have to go back to the original Coulomb's equation or the original Coulomb law. That means the traditional way of writing down the integral of rho of r prime. You remember, this is the Gauss law, right? This is the Coulomb's law. This is what you will have to go back. When you do not have any information about, about the symmetry of the electric field, then you have to use this expression. You have to use this expression for the electric field. Gauss law will not come into picture. So the distinction, or where to use Gauss law, where to use Coulomb's law, should be clear to you. This is very important. Okay. So I will erase this portion. So now the point is clear, right? You should know the symmetry of the electric field for a given problem, then only we can proceed. So now we are now asking the question, do you have any idea about the direction of the electric field for a point charge? That is what we mean to say. And now we are going to provide the answer. Yes, the electric field is going to be like this. That means the electric field will be in all possible directions, that will be going like this, which means that basically you are trying to draw the electric field lines due to the point charge Q. That is the meaning. So this is the statement of saying that beforehand means even before knowing what is the electric field magnitude of that, I know the direction. That means you know the symmetry. This is called symmetry. So you already know the electric field directions. That means it is spherically symmetric, and therefore when you measure the angle between this one and that one, when you measure the angle between electric field and surface, you see here you are trying to measure the angle between the electric field line and then the tangent drawn to the surface at this point. You'll have to draw a tangent, then only you have to measure. So this is the tangent that you draw. After drawing the tangent, here also you draw the tangent, and then, you draw it correctly. If you draw this tangent like this, then you take the measurement, then it will show a perpendicular. So our conclusion is this: electric field is in the radial direction in the spherical polar coordinate system. Now you are drawing this arrow, right? You are asking the question, what is the unit vector? These directions. The unit vector is AR cap. This is also AR cap. This is also AR cap. So all possible direction that you are going to draw, they are all known as AR cap in the spherical polar coordinate system. And therefore this E is to be written down like this. This is very important. Then dot the surface area of the sphere that we are going to have, or we can always write down what is the quantity corresponding to the ds. Okay, so you write down the corresponding surface element in the case of the spherical polar coordinate system, which is nothing but you can write down that r is the radius of the sphere. Then I can write down r times d theta. R times d theta, that is on one side. Then corresponding to the theta side, then you will be having r times sine theta. Then you have a d phi. And this is the surface element, but the corresponding unit vector will be AR. And this is what you'll have to evaluate and then substitute the limits here. So here you'll have to note down that here r is constant, theta will be varying from 0 to pi, and then phi will vary from 0 to 2 pi. So these points I already explained. The moment you are going to consider the spherical polar coordinate system, these are the limits that are going to come, and therefore we can now evaluate this expression. And since it is since you have a d theta here and a d phi here, you can now understand that this is actually a double integral where these limits have to be substituted. And now if you see this, E is a constant, you see E is a constant, R square is also constant. So let me therefore take outside E constant, R constant. So R square is there. Then you have a AR, this AR dot AR, so that becomes 1. Then you have an integral theta equal to 0 to pi. Then you have an integral phi equal to 0 to 2 pi. Then whatever is left out there. So what is left out now is you have a sine theta, d theta, then you have a d phi. And this integral is quite simple because d phi alone you can finish the integration. So then you get E into R square into integral theta equal to 0 to pi. This is sine theta d theta. Then the entire thing, integral of the d phi gives you 2 pi. Because 0 to 2 pi limits are there. That is why it gives you 2 pi. So and that will give you, so once you simplify this, this integral is actually minus cos theta. I'll do it separately. Minus cos theta, and then if you substitute the limits 0 to pi here, then this gives you minus of cos pi minus cos 0. So it is minus of cos pi is minus 1, and this is also minus 1. So I will be getting 2 here, right? So that gives you 2. So I'll get E into R square into 2 into 2 pi. So that gives you 4 pi. This is 4 pi, then there's an R square, then there is a E here. So let me write down the E outside, will be equal to, this is your LHS. So you have now completed the evaluation of the LHS and you already have the RHS there. I think you remember what is RHS and we can substitute. The right hand side is how much? The right hand side is here. Q divided by epsilon naught is the RHS. So therefore let us substitute that. So this implies LHS equal to RHS. You are to write like that, which means that this quantity you now write down, 4 pi R square into the electric field is equal to, the right hand side is given by Q by epsilon naught, and that tells me that the magnitude of the electric field is equal to Q divided by this 4 pi R square is going to come down here. So I'll put this 4 pi R square. Then you have an epsilon 0. So this is the one which we are rewriting in our familiar form, namely E equal to 1 divided by, so let us write down the constants, 1 divided by 4 pi epsilon 0 into Q by R square. So ultimately what happens is that you are getting a result which is familiar to you. So that is why we are choosing this kind of example. If you choose this example, the advantage is you already know the answer, and then you can realize how this particular Gauss law is working. If you take some complicated problem, we will get some answer, that is fine, but you do not know how the method works. You get an answer, that's fine. But now what happened is this particular expression 1 by 4 pi epsilon 0 into Q by R square is something which is quite familiar to you, and you know that this is the electric field due to a point charge as given by Coulomb's law. So we are actually getting this back. How we are getting this back is using the Gauss law. So you are now able to appreciate how the Gauss law is working. But there is a downside of this. There is a negative point. Negative point means the disadvantage is that the system should have symmetry. Some symmetry should be there. It should be cylindrical symmetry, spherical symmetry, some kind of Cartesian, box-like symmetry. Some symmetry should be there. If there is no symmetry at all, for example, absolutely no symmetry at all, then this Gauss law is totally not usable. It is not at all helpful. You have to revert back to your integration in the Coulomb's law, and you have to perform the integration as it is there in the Coulomb's law to get the answer. So this is a very important point that you'll have to remember when Gauss law is applicable and when Coulomb's law is applicable. And the important point is that I have performed this integration explicitly. Okay, in some of the books, if you see, they will not do this particular step, and instead of that they will say that the surface area of the sphere is given by 4 pi r square, and then the job is over. Okay, that is not a good idea, because all the time you are not going to have the sphere. Okay, therefore you should also know what is the integration to be performed in order to finish this integral E dot dl. Okay, if I say that the surface area of the sphere is 4 pi r square and proceed further means, then what is the integration you have to do? There is no integral at all. So those points should be clear. It is not that we want to complete the problem in few steps and then jump into another problem. That is not our aim. Our aim is we are interested to evaluate the integral in detail, and we need to know where are the important steps coming into picture. This is very important step. You'll have to carry over the dot here when you are performing the integration. First point. Second point is you must have a unit vector before the dot, and there should be a unit vector after the dot. So this is the dot that you have. This is after dot and before dot. There must be unit vector available. If you don't have a unit vector either on the left hand side or the right side of the dot, then this Gauss law cannot be used. That is what is known as the symmetry. If you know the symmetry of the problem, you will be knowing the direction of the electric field beforehand. Beforehand means even before getting the solution to the problem. In such a situations, only you can proceed further for the evaluation of the integral in the Gauss law. Once this is clear, then automatically this unit vectors will be dotted here, and that will get simplified. The rest of the integration has to be carried out in whichever coordinate system you are choosing. In whichever coordinate system, okay, it's independent of any coordinate system. And since we have drawn a diagram like this in the sphere here, this particular surface is known as Gaussian surface. Why it is called a Gaussian surface is it is the surface used to evaluate the integral in the Gauss law. It is the surface used to evaluate an integral in the Gauss law. That is why it is called Gaussian surface. This surface is not a physical surface. Physically, you don't have any metallic surface or some kind of insulating surface, nothing. It is not. It is completely a mathematical object, which means a geometrical surface. You cannot see a geometrical surface. Okay, you can't take a photograph. You can only have a point charge, and then the surrounding surface is not visible to you. It is a geometrical construction. That is why here I have used the word. So you have to be careful in understanding everything that is written here. So evaluation of the right hand side is always straightforward. There is no integration at all. What is the total charge present in that sphere? That's all about it. If numerical problem is given, you simply add all the charges. Okay, it doesn't mean single charge. If you have 25 charges, add all the 25 charges, plus or minus whatever it is. You take the numerical addition of all of them, and then that's it. That is a Q enclosed. So only the left hand side only you will have to evaluate in this expression, so that you are getting this answer. So this is the answer. So frequently you will be asked to calculate the electric field due to certain charge distributions. Okay, so this particular example illustrates how Gauss law can be used effectively. Okay, we can repeat it for many different varieties of problem, but however, this example gives you an illustration of what is going on, and the same thing can be repeated for other problems. So till now, our discussion has a considerable amount of information on the electric field, which is basically coming from the Coulomb's law as an experimental evidence. The second important component of the electromagnetic theory is the magnetic field, which is also once again experimental evidence observed by Biot and Savart. And the experiment and other things you already know, that you have two current carrying conductors, and then when two conductors are having currents in each of them, then they attract each other or they repel each other. So there is a force of attraction or force of repulsion between two conductors. Generally, they are taking two conductors that are parallel to each other, so that calculations are simple. So that gives you an indication. What is an indication is that how there is a repulsion, or what is actually responsible for repelling each other or attracting each other is not the current itself. Current itself is not going to attract. So the conclusion made by the Biot-Savart is that whenever a current is flowing in an electrical conductor like a wire, then surrounding this wire a field is generated, and that field is what is known as magnetic field. So that was the experimental observation of the Biot-Savart, and then they have given an expression like this, which is let me write down an expression which is familiar at the level of higher secondary school, where you write like this: the dB means a small amount of magnetic field generated due to a small length of the wire. That is why it is a differential element, which is given by the constant that is only due to the SI units. Then you have this expression I times dl times sine theta divided by r square. So this is what usually you learn at the school level. And now this equation doesn't contain information about the vector. And you see here that our aim is that we will have to first of all construct in vector form. That is first thing. Second thing is we will have to construct in terms of current densities rather than current. So these are the two reasons why we will have to start with this, and from here we can move further in the modification. Modification means appropriate to the experimental observation of the magnitude and direction, we can now write down an appropriate equation. So this equation is a scalar equation. You have a scalar equation, then plus information about the diagram or information about the direction of the magnetic field is generally explained separately. Separately means like it is detached from the original Biot-Savart law. This equation itself doesn't have that information. So instead of that, what happens is they used to give, so generally this is how you learned. So this is what we have to combine. What you learn is if the current in the wire is like this, then the magnetic field will be generated in this particular direction. So your direction will be attached like this. So that will be the magnetic field if this is the current. So which means that there is some information here in the form of an equation, which is a scalar information, and this particular information provides something about the vector. So the knowledge about the vector goes separately, and then the knowledge about the scalar is written down separately. This is how the Biot-Savart law is introduced in the school. So now we need to combine both of them and then write down an appropriate equation. That is the first point. And second point is we are also interested to write the expression in terms of the current density rather than current. So these are the 2 points that we need to know, and therefore keeping this in mind, okay, that should be the objective. So keeping that in mind, so let us try to combine this information into an appropriate vector equation. So the equation looks like this. So it's not difficult. Let us write down this equation. But before writing down the equation, something is clear. What is clear? Let us see. If this is the direction of I, okay, this is the direction of I, then the direction of B is perpendicular to that, because you'll have to draw a tangent to the circular path. There is a circular path, right? Magnetic field lines are always closed. Magnetic field lines are always closed. So that is why it looks like this. And at this particular point, if you draw any tangent, it will be down like this, and which is perpendicular to the current. So our understanding is that the current and the magnetic fields are perpendicular to each other. And in order to represent that, naturally a sine theta has already come into picture. So you already know why the magnitude is having sine theta, and ultimately it turns out that the formula for the A cross B is actually AB into sine theta. So which means that this sine theta in the equation gives you a hint that there should be a cross product coming into picture. That is the meaning. So whenever A vector is like this and whenever B vector is like this, this is the thing. And if you can complete the rest of the thing, then it appears as a surface. It is a part of the floor. it is part of the floor, it looks like that, then the perpendicular to that means the normal to that particular floor is the direction of A cross B. So this is the basic geometrical information which you are already familiar. So our conclusion, or what is that we are trying to say is, some object is perpendicular to something, right? And that is what we have here. Here one of them is horizontal, like this, means the magnetic field is perpendicular to that. Downward or upward, that is okay, that will decide plus minus, but ultimately it's perpendicular, and therefore the A cross B will represent the resulting quantity which is perpendicular to the plane containing A and B vectors. So our job is now clear, that you will have to identify what is this A vector, and then you will have to identify what is this B vector. Okay, small a, small b. They are not magnetic field. These are mathematically we write some vector A and B. So that is an idea. Idea is clear, that some kind of cross product has to enter into picture. So that is clear. And instead of dB, I am now writing only B. What is the meaning? That dB can be brought into B because we can perform the integration. That's the meaning. So the rest of the thing, let us write down that this is the quantity. And since we are evaluating B here, the integral has to be written down. Now here, when you are going to combine the two quantities in such a way that there is a cross product comes into picture, we generally write this. So let me explain the explanation I will tell, but how it looks like, let us see. This is I cross R cap divided by, so this R square is written as R square, then there is a dl prime, where this integral has to be performed over the wire. The integral has to be performed along the curve of the wire. Okay. When I write dl here, you will have to understand what is dl. Dl is a small length or elemental length. Length of what? Length of the wire which carries a current. That is what is the meaning. Now you can see considerable difference here, and we are going to use the script R here, because script R is the one which I have been explaining from the beginning. It's very important. Script R represent, maybe we will write down once. Script R is actually R minus R prime, and you know what are this R and R prime, and therefore this quantity should be equal to R minus R prime vector divided by the modulus of that. So this is the R cap that is coming into picture, and what is this R and what is this R prime is already explained in the very beginning of this lecture, where you have to choose a coordinate system. Okay, maybe instead of referring to the old lecture that has been done long time back, okay, maybe I will draw a small diagram so that it will look easy for you to understand. So this is the place where you are going to have some current. So some current is flowing in this particular object. And what is this object? It can be any object. Okay, you take some kind of a metallic piece, and then you can pass the current through this. So this is the place where the current is flowing. You take a small element of that is called elemental bit, or a small bit of that. And then we are going to refer to a coordinate system. So you always attach a coordinate system, 0 here. And if you are going to draw a line from the origin of the coordinate system to the place where there is a current element, okay, that object is what is known as R prime. So that is the meaning. And then I want to calculate what is the magnetic field at this point. I am interested in calculating the magnetic field at this particular point. Then what you do is, you once again draw the line from the origin of the system to the place where the magnetic field is to be calculated. This is what is known as R vector. And then you draw another line from the current element to the place where magnetic field is to be calculated. This quantity is the R minus R prime. And that's all about it. So you know what is this quantity, and this is exactly what is known as the R, script R. So the concept of the script R should be very important, and where you can represent XYZ and origin. So this particular diagram is very important, because only when you draw the diagram you will be in a position to explain the small r and then small r square coming into picture, and where the dl prime represents elemental length of the wire. So here I have drawn the most general one, namely you have a volume. Instead of this, you can also always draw a wire like this. So that's a wire. In this wire, some current is flowing into the system. I say that I current will flow. Then if you take a small bit of this is a small bit of that, that is what is known as dl prime. And other things are same. You draw this particular coordinate system, and from here to here you draw this a line, and then you draw from here to another place where magnetic field is to be calculated. So if you are going to complete this particular line like this, okay, if you are going to draw like this, and then I will be saying that this is the place where I am interested to calculate the magnetic field B of r, and this is the origin of the coordinate system. This will be the r vector, this will be r prime vector, so this will be equal to r minus r. So you can see that either you can have a wire, that is why I am redrawing once again. Here you have a wire, and here you have, instead of wire, you have a very thick object, or we say bulky material. So why you should take only wire? You can also take a very bulky material which doesn't have a proper shape, but it can be made up of a metal. So if you pass current through that, a current will pass through that. Only wire should not be there. It can be any material such that it's a metallic material, generally electrical conductor, but its shape need not be in the form of a wire or in the form of a rod. It need not have any shape. Okay, let it be any arbitrary any shape, then the current will flow. That is why I have drawn this particular one, and therefore an arbitrary shape is what is represented generally by the symbol tau. Tau means some volume, arbitrary volume, so that is the tau, and therefore instead of saying the wire, we can always write down the arbitrary volume. So let me therefore write down how the same equation can be rewritten once again. So we are interested to write the Biot-Savart law like this: mu naught G divided by 4 pi due to the SI system of units. Then if you are going to consider the current density into the system as J of r prime, then we can write down that this is J of r prime. That is the amount of the current density that is flowing into the system. Now you understand why density has to come. Whenever you have a bulk material, then always current density is most appropriate to discuss rather than total current. Total current is not convenient. Density is only convenient. Similarly, in the case of electrostatics, charge density is convenient, not the total charge. Okay, total charge can be always calculated, but charge density and current density are the convenient quantities for the evaluation of the integral. Therefore, this is the expression. Then other things are same, namely the script r unit vector divided by the script r square. Then the integration has to be carried out over the entire volume. So therefore, I will say that now this integral is over the volume of the material. Now I am not writing wire. So that difference is what you'll have to observe, that now wire is not there in the system. So this is how you will be writing, and this particular equation is not what is known as the Biot-Savart law. So basically it is the same experimental observation which is quite familiar to you, but now we are writing in a particular form, and this equation contains all information about the magnitude as well as direction. Okay, now you don't have to say that I am going to follow some kind of left hand thumb rule or right hand thumb rule. Nothing is required. Okay, this equation tells you both the vector nature and the magnitude of the magnetic field. So which means that this kind of representation, a separate diagram, is not required in order to explain what is the direction of the magnetic field. So this is very important. So there is nothing difficult here. It is only that we are managing to write down the sine theta. Now the sine theta is absorbed, right? A cross B formula means automatically sine theta is taken care. And very important point is this script r. So now let me write down that, so that this is required in case if you are interested to perform the calculation. So where the script r is generally written as, it is x minus x prime into the unit vector. And why it is x minus x prime? That is, those things are already known to you because we have already explained in electrostatics. there is an r minus r prime, right? Because of r minus r prime, you are now writing the three components. The three components will be x minus x prime along the x direction, and then we have a y minus y prime in the y direction. Then we have the z minus z prime in the z direction. So this is the meaning of the script r. If it is the case, then what will be this? So that will be equal to square root of the entire thing, that you will have to take the squares. As usual, you know how to take the magnitude of that. It is x minus x prime whole square plus, you repeat it for the y and z component, and that's all. And therefore, and this means that we can always calculate this equal to equation 1 divided by equation 2. That means I will write down that this divided by this. So these are the things which are very important, that they have to be substituted in this place in case if you are going to use the Cartesian coordinate system. This way, because this is written explicitly in Cartesian. In case if you are going to use the spherical polar coordinate system, then you'll have to use the corresponding vectors. So these vectors, whatever we have written here, these two things are valid for the case of Cartesian. And the last one, this is valid for all coordinate system. This will not change. Okay, for all coordinate system, this expression is valid. Only the first two things explicitly written down for Cartesian, because sometimes you may be numerically doing some problem solving in the Cartesian system, in which case you will have to use this formula. So that is first thing. The second, there are further, now let us go to the further detail. Now comes the interesting point. Now we know the following things, namely the Coulomb's law is known to you. Now we have rewritten the Biot-Savart law in a vector form, so that is also known to you. And in addition, in the previous class, we have also seen that the Faraday's laws can be rewritten, which is of course only for refreshment. I will tell what is written in the last class is that if you are going to have the time varying magnetic flux, okay, you already know what is the Faraday's law. That's what I am writing. That is the EMF generated. So the EMF generated, EMF means voltage generated in a particular circuit, is given by the time derivative of the magnetic flux. This is the magnetic flux. Flux means number of lines that you are going to show. See, if an electric field, if you are going to show the electric field line like this, if this is a plus q there, what is the meaning of the flux means how many lines you are considering? 1, 2, 3, 4. If you are going to consider only 4 of these lines, and any electric field that is present here, these things, this portion I am not going to take. If it is the case, you say that this much amount of the flux I am taking. So that flux is what is written down in a symbol, either phi or phi, something like that. That is called flux. So flux tells you exactly the number of how much amount of the field lines are present in the system. Okay, that is called flux. Flux density means you'll have to take the entire flux then divided by the area. So if you calculate the magnetic flux by total area, that is the magnetic field. So these basics are already known. Okay, that this is already defined in your school itself. So therefore you should know that. So total number of magnetic field lines divided by the area. Area means this area. So whatever area that you are going to consider, within that area, whatever line penetrates into that, then if you calculate that, then that is known as the magnetic field. So the definition is like this. So it is easy to remember like this. Phi is equal to area is A, B is the magnetic field. So phi equal to AB is something that you can easily understand, and where you can feel that the component has to be perpendicular, because the confusion will come if I am putting the vector here. As I already explained, whenever a vector quantity is crossing a surface, you have to take the normal component only. Okay, otherwise there is no meaning for that. Only normal component of the vector should be taken into consideration when you are evaluating this. Okay, then only this particular expression is valid. So let us keep these things. Okay, namely the three equations. So the Coulomb's law is 1, Biot-Savart law is the second one, and then the Faraday's law is the third one. So we have three of the experimental evidences are right now available. Now the interesting point what we are going to do in the next class is that what will be the connection between all these things, whether these three experimental observations are completely independent of each other or there is any connection. So that information will be available if you perform the vector operations on these equations. So that is what we are going to do in the next class. But before that, I would like to mention a small point that you just note down, because this equation is there, right? So I want to write down here itself. So the divergence of this quantity r by r square is equal to 4 pi into delta cube of r. This is some result. If you are going to evaluate the divergence, you don't have to worry about how to evaluate the divergence right now. So, but instead of that, you can keep this result, that curl of r cap by r square. You know what is r cap? This is the r cap. You know what is r square? R square means the modulus of a then square. That's the meaning of this r square, and this is equal to 0. So these two results are important. So let us write down here itself instead of going to the next class. Why? Because these are connected with these equations. So that is why I want to write them together. And there is nothing to worry about this delta function. Okay, delta function means it is 1 actually. So right now, no need to worry about the delta function. Basically, it means 4 pi into 1. That's all. You can always write 4 pi. It is in principle, that is the meaning. So for the time being, this is the information that you need to know, that the divergence of r by r square, r cap, the cap is important, not this vector. Okay, this is a cap, unit vector is this one, and if you take the curl, it is 0. These two results are important. If you are now in the next class, we are going to perform some calculation. So for that, these two expressions or the results from vector calculus, we are going to use it. So we will continue therefore in the next class.